thank you very much, the organizers, for this invitation. I'm a postdoc at the São Paulo State University in Brazil, and I'm working on planet formation, basically. So today I'm going to talk a little bit about the solar system formation. So basically I'm going to talk about a few episodes of the formation of the solar system. I'm going to talk about the formation of the inner solar system, the formation of the ice giants, basically Uranus and Neptune, and also I'm going to talk about the solar system dynamical instability. So you know already from the previous talks that planets form in disks, and these disks, they typically last a few million years, maybe less than 10 million years. So basically the gas disk lifetime is short, and much of the planet formation happens during these first few million years. So let's take a look at the stages of planet formation. So planet starts to form from grains that grows to probably to pebbles. Pebbles, they should be particles of centimeter to millimeter size objects. These pebbles, they feel gas drag. They typically spiral inwards, as Nader said before. If they can clump in some specific regions of the disk, then you can eventually form big objects that we call planetesimals. Planetesimals are basically kilometer-sized objects. So if these planetesimals can continue accreting pebbles or growing by mutual collisions with other planetesimals, they can grow to planetary embryos, and planetary embryos can grow in two different ways. If the gas is still around, so if they are big enough, they grow to, for example, to a few Earth masses, or maybe 10 Earth masses. If they are in the disk, they're going to interact with the disk. They are going to gravitationally interact with the disk, launch these spiral waves, and they're going to migrate. We call this mode of migration type 1 mode. If they have time to become a gas giant like Jupiter, they become massive enough to open a gap in the disk, and they start to migrate in the type 2 mode. After the gas in the disk is gone, probably after a few million years, maybe 3 million years. So no more gas in the disk, you have a few planetary embryos. Their masses depend where they are and how much mass you had from the beginning to form them. So you can imagine that the inner region of the solar system, you have something like maybe Moon to Mars size embryos. In the other part of the solar system, beyond a few AUs, you could have something like a few Earth masses of size in embryos. And these bodies, they are produced during this runaway and oligarchic growth that Nader talked about. So after the gas is gone, you can have collisions because there's no dissipative effect to keep their orbits cold enough. They typically cross orbits and collide, forming planets, like the Earth. So in the first part of this talk, I'm going to focus on the inner solar system. So I'm going to explain how these terrestrial planets form and how the asteroid belt form. So let's take a closer look at the inner solar system. So that's what we got. We have 4 planets and the asteroid belt. Let's take a closer look at the asteroid belt. This is the structure of the asteroid belt. So each one of these dots is one asteroid larger than 50 kilometers in size. And if you look at the inclination and the centricity versus semi-major axis, the belt is located between about 2.1, 2.2 AU to about 3.2 AUs in the inner solar system. And the eccentricity distribution ranges from basically 0 to 0.3. So they have very eccentric orbits. And the inclination from 0 to about 20-25 degrees. So the belt is dynamically excited. Because if you compare with the planets has a typical eccentricity of a few %. That's much more higher eccentricity than inclination than the belt. So the belt is dynamically excited and also is depleted in mass. If you compute the total mass in the belt, you're going to have something like 5 or 10 to minus 3 Earth masses. That's more than 1,000 times more depleted than the terrestrial region. So one of the questions that I want to address from this in the next slide is, why is Mars so small? If you compare Mars with the Earth, Mars is 10 times less massive than the Earth. So another issue that you have in the solar system that Nader already discussed about is how did the Earth got its water? And why the asteroid belt look like this? Why it's so dynamically excited and mass depleted? But the asteroid belt is not only this. You have another feature of the belt that's quite important. The belt is divided in two. The inner part of the belt is dominated by S-type asteroids that are basically water-poor asteroids. And the outer part of the belt is dominated by C-types. So a mode of terrestrial planet formation, to be consistent, has to reproduce these two features of the belt, including those previous ones that I discussed before. So let's take a look at the classical mode of terrestrial planet formation in the solar system. The classical mode assumes that you have Jupiter and Saturn in the system. They form near their current orbits. And you have some planetesimals that are already formed everywhere in the solar system. So these planetesimals, they grow to planetary embryos. As I said, the inner ones are smaller than the outermost ones, just because you are in the outer regions of the disk where you have probably more volatiles. So one of these lucky planetary embryos becomes Jupiter, and then this population here becomes the other ice giants, and then finally, after this process is complete, you have the formation of the terrestrial planets. So in this meantime, the gas dissipates, and boom, you form the terrestrial planets. So that's the view of the classical scenario of terrestrial planet formation. So this was just a cartoon, right? But here's a real simulation, and we have Jupiter and Saturn sitting beyond 5 AU, and we have a population of planetary embryos and planetesimals. So these guys here, the big circles, they are like moon-sized to Mars-sized objects, and the small ones, they are kilometer-sized or like asteroids. So we're going to assume that the gas dissipates because this is the late stage of accretion. There's no gas in the disk. The disk is dissipated, and then this body starts to interact with each other and grow by collisions, and also to scatter each other to higher eccentricities and inclinations. So this is what happens. So the color here shows what we assume it to be water-poor objects from inside a few AU and water-rich objects in that region. So because of this dynamical excitation, there are collisions, and then some bodies are formed in the system. In this case, we have 3 planets. So one sitting near 0.7 AU, another one near 1 AU, and the third one near 1.6. That looks like near the current location of Mars. But if you compare the masses of these bodies that are represented by the size of the dot, what we see is that the planet that's formed around 1.5 AU, this one, is larger than this one. So this is the typical outcome of the classical model of terrestrial planet formation. So if you run many simulations like this and plot all them together in a plot, that's what we got. Here we have the masses versus some measure axis of a few simulations plot together. So you have the square that represents the terrestrial planets and the circles that shows the simulated planets. So if you compare how the planets are formed around 1.5 AU, they are typically much larger than Mars. So that's what we call the small Mars problem of the classical scenario of terrestrial planet formation. So how to solve this problem? So this problem has been around for more than 20 years. And then in 2009, Brad Hansen proposed this idea. Rather than starting one simulation with a very wide disk like this, let's truncate the disk and put a lot of material in a very narrow region. So what he did was, let's start with a disk that narrow, include 2 Earth masses of solid material in that region, in embryos and planetesimals, and let the system evolve. So in this case, Mars is formed because one embryo that gets ejected from this region to beyond 1 AU stop growing because there's nothing to accrete. So Mars, in this case, the small mass of Mars is an edge effect because there's no mass to Mars grow. That's the reason maybe that it stays small. So what the Hansen shows is that the small Mars problem requires a severe mass deficit beyond 1 to 3 AU. We have to deplete the inner solar system to get Mars right. So how can you do this? So one idea is, so the belt was born massive and get depleted by a mechanism. Then I'm going to propose one mechanism later. So let's assume that this is the disk that the inner solar system is forming from. You have the sun, you have the inner material. That's basically, let's say, imagine inside 1.5 AU. The total amount of mass in this region could be 2 Earth masses. And then you have the asteroid belt region that has also 2 or 3 Earth masses. So you could form Earth here. But you cannot have this amount of material, otherwise you're going to form up Earth, and you want to form Mars. So you have to deplete the belt. And beyond a few AU, you have the material to form the gas giants. So a second solution is, maybe the belt was born low mass already from the beginning. So that's the reason Mars is small. You don't have to deplete it. It was just formed with low mass. So you can have maybe 2 Earth masses of material in the inner region to form all the terrestrial planets. And then you just have a little bit of mass in the asteroid belt. So that's what we see today. And you have a lot of mass beyond a few AU. The third solution is, maybe the belt was born empty. There's nothing there. And then we refill it with material from different regions. So that could be material coming from this region and material coming from this region. And I'm going to talk about each one of these scenarios in the previous slides. So let's first start with the belt was born massive and then you have to deplete it. How can you do this? So the idea where you have a massive belt and then you deplete it is called the grand tack scenario. So you start with a disk very wide with a lot of mass, and then you want to create a very narrow disk. How do you do this? Let's put Jupiter to do the work. So if Jupiter migrates up to 1.5 AU, and then it truncates the disk, and then you have to bring it back. So you're going to see how this works. So this is the basic idea of the grand tack scenario. You need to create a truncate disk, and then you use giant planet migration to do it. So here's a simulation of the grand tack scenario, where we have Jupiter, Saturn. Here we have eccentricity versus inclination on the top, and the head dots are the planetesimals or the planetary embryos of the simulation. So you have gas around because the planets are going to migrate because they are interacting with the disk of gas. They are migrating the type of migration, type 1 or type 2 or type 3. So let's say how this migration happens. So Jupiter starts to migrate, then it pushes material to inside 1.5 AU, and then it's capturing resonance with Saturn, and they migrate back. When they migrate back, they enter this region where we have these blue dots that means like represent the water-rich bodies, and these bodies, they are scattered towards the terrestrial planets. So if you look at the kind of disks that we have here, it's very similar to what has been proposed by Hansen. Typically, this ends being like ends with about 2 Earth masses of material to form the terrestrial planets. So let's see how the grand tack works in a little bit more of details. So the idea is like this. So have time, have some measure axis. Jupiter's form, and then it starts to accrete gas when it reaches about 10 Earth masses. When it reaches about 50 Earth masses, it starts to migrate really fast because in the type 3 migration mode. When it enters in this region, it becomes massive enough, it opens a gap, and the migration speeds decrease. It becomes lower, and it enters the mode migration type 2. In the meantime, Saturn is forming the disk. Saturn is forming. Then when it reaches also 50 Earth masses, enters in the type 3 migration mode. And because it migrates faster than Saturn, than Jupiter, they meet each other in this way. And then there's a capturing resonance, and they have reverse migration. This is an effect that is observed in hydrodynamical simulations. So that's what happened. They start they migrate up to a few AUs, maybe up to 1.5 AU and then migrate outwards back to beyond 5 AU. And if you look at the terrestrial planets that you can produce in the Grand Tack scenario, that's how they look like. So you have here again masses, same measure axis. The squares are the terrestrial planets, the real ones, and the triangles are the simulated ones from the Grand Tack simulation. So we can see that there's no small Mars problem here. So typically the bodies are the same mass than Mars, those that are formed around 1.5 AU. But there's an issue. The Grand Tack invokes a specific migration history for the giant planets. It's not the only one possible. So here I have brought together from Zhang and Zhang in 2010 and results of a few simulations with Jupiter and Saturn migrating the disk. So they are released to migrate at 200 orbits, that at the time 200 actually, and that's what happened. So you can compare the pairs of colors. For example, if you compare the head for Saturn and head for Jupiter, you can see that we have a disk with a given profile. I'm not going to details here. And for this disk, it can migrate, both planets can migrate outwards. That's what it shows. But if you change the slope of the disk to be R2 minus 4 over 3, so the migration is not that fast anymore. So it hits we don't get so far from the inner regions of the disk. For more shallow disks, so there is no outward migration. We compare the pink colors here. So for R2 minus 1, rather than migrate outwards, both planets migrate inwards. So we could have all this type of migration for Jupiter and Saturn, the disk. And the Grand Tack is just one of the possible ones. So let's talk now about the belt was born with very little mass. So how to produce a belt where you have very little mass in this region and you have some amount of mass that's much higher than that. So that's possible if you invoke gas drag and radial drift of solids. So imagine that you have a protoplanetary disk and have disk of solids and have small particles here. And these small particles may be kilometer size or centimeter size. They are spiraling inwards because of gas drag. So if they migrate from this region to this region, so basically you change the gradient of the surface density of the disk. So something like this. You could start with a disk that looks like this, and then because the bodies migrate from this region to this one, and if you can pile up them there, then you get a mass distribution that looks like this. So because there's very little mass in that region, so the belt is naturally depleted. So that's one possible solution. So just to make it clear, so you could start with a high mass belt that could be represented by a disk with a power law given by this expression. So the mass distribution follows this profile. Or you can start with a low mass belt. If you start with a high mass belt, you need the Grand Tack to deplete the disk. Otherwise, you're going to fall in the Mars small problem. So let's perform simulations with a low mass belt and see what happens. This is maybe a alternative solution to the Grand Tack. So simulations with a massive belt. Let's just redo the exercise that we did before. So here we have a simulation. We have again a very massive belt that's very similar to what we get from the classical scenario. So there's a lot of mass in the belt. So x equal to 2.5. The distribution of mass is like this. Is not that steep. So you have here again the simulated planets and the real ones as triangles. If you compare the real planets with the simulated ones, we can see that we still have the Mars problem here. So planets that are formed around 1.5 are maybe at least 5 times more massive than, maybe a few times more massive than the Mars. Let's compare what kind of asteroid belt we get for the simulations. So here we have eccentricity, inclination, and the gray region here represents the asteroid belt. If you want to have a good model of terrestrial planet formation, you have to fill these two great regions with asteroids. That's what we get from when you look at the asteroid belt today. So this is what we get. When you look at the eccentricity distribution, you can produce some very exciting asteroids in this region. So if you look at the asteroid belt region in terms of inclination, it's not clear what's going on. So what we did was, let's apply a statistical test and compare these populations of asteroids in the simulation with the real one and see what we get. So we know already from this case, it's visible, it's clear that we have a small Mars problem here. So if you compare the distribution of asteroids with the real belt in terms of eccentricity distribution, so they match quite well. We cannot reject these populations as similar to the asteroid belt today. But if you compare this population with the asteroid belt in terms of inclination distribution, they don't match. Basically, you can see that here that you have very high inclination asteroids in that region. And this is because you have these large embryos in the belt. And this is also bad. Imagine that you had in the past a very massive embryo in the belt. So this embryo should open a gap because you're going to eject the small asteroids away. And so you don't see this kind of gap in the asteroid belt today. So that's the one very strong argument against having starting simulations with very massive asteroids in the belt from the beginning. So because it's really hard to remove them later. Even if you remove, you have to remove fast enough to make them not create gaps in the belt today. Because if they create gaps, you should see them today and we don't see. So the only gaps that we see in the asteroid belt today come from mean motion resonances with Jupiter. So what we did, let's start with a very massive belt. Something like this. So there's very little mass in the belt from the beginning. What we got was like this. So you can match quite well the four terrestrial planets. You can match Mercury, Venus, Earth, and Mars. So you can see there's no small Mars problem in the simulations because there's very little mass in the belt. Mars is not growing because there's no mass to accrete. So, but let's look at the asteroid belt in this simulation. So you should fill all this gray region with black points. And this is not what's going on. And why? Because there's so little mass in the belt, the mutual interaction between these bodies that are there are too weak. So they are not strong enough to pump up inclinations and eccentricity to the level that we observe in the belt today. Simple. There's no mass in the belt to scatter planetesimals up to 20 degrees of inclination and up to 0.3 of eccentricity. So what's going on here is the following. You can produce Mars in the very low mass belt, but you cannot excite the asteroid belt because there's no mass there enough to pump up the inclination. So when I got this result in 2015, I thought, oh, the Grand Hack is the only solution. This is the most viable solution because it's not going to be easy to excite the asteroids in this case. And then I was running a bunch of simulations and just happened if one of them work. And I was puzzled to understand what's going on. And I'm going to explain in the next slides. So basically, the takeaway messages from this previous slide is the following. We have Mars. To produce Mars, we need to have a mass deficit. But to get the asteroid belt right, you have to have a lot of mass, then it can self-excite to the levels that we observe today. This is a puzzle because imagine you have to have low mass for the belt, but have to have high mass for the asteroid belt. Then there's one missing ingredient in the simulations, the orbital chaos. So we know that everybody here is familiar with the butterfly effect, where there's a very little perturbation somewhere can cause a disaster somewhere else, right? So that's what maybe happened to the solar system. So you have Jupiter and the asteroid belt, the giant planets actually, Jupiter and Saturn. And because they had a chaotic evolution, eventually during the start of the solar system that we propose, they were like dancing like this and causing this to the asteroid belt. So let's see a simulation showing this effect. So here is one case. Well, the point is we want to excite the belt, right? If you start with a very steep disk or very low mass belt from the beginning, you can get Mars right. But then the asteroid belt is dynamically cold. You want to excite it to the levels that we see today. So that's what the ingredient that we are looking for. So here are the simulations where we have Jupiter and Saturn in a regular configuration. So the belt is between, let's say, 2 and 3.2 AU in that region. So that means that to reconcile this low mass asteroid belt with the real the inner solar system, you have to excite all this region here up to 0.3 of eccentricity, and all this region here up to 20 degrees or so. So let's see what happens. So the simulations has Jupiter and Saturn fixed beyond a few AUs, beyond 5 AU. So, and you can see that it's not working. The only excitation that we see are these little bumps here that are associated with resonances with the giant planets. So that means that this case cannot excite the belt to the levels that we see today. So it cannot save the model where we start with a low mass asteroid belt. So, but the story changes if you start the simulations of chaotic Jupiter and Saturn. So let's see how it changes. So you can see that the level of excitation that we get in the belt now, it's consistent with what we observed, both in terms of eccentricity and inclination. So if you have a low mass asteroid belt from the beginning, but if Jupiter and Saturn, they had a chaotic evolution, then you can excite the belt to the levels that we observe today. Just to compare the kind of dynamical evolution that we have for Jupiter and Saturn in these two simulations. So the regular one and the chaotic one. So here is the period ratio of the planets. They are basically near the 2-to-1 mean motion resonance. So basically means that Jupiter is going twice around the Sun and Saturn is going just one. They are very synchronized orbit. And here you have eccentricity for both cases, and inclination and the resonant angle. But that doesn't matter much here. So what we can see is that there's just very little oscillation in terms of eccentricity and inclination that are able to amplify the effect on the belt. So that's because you create new resonances in the belt. I'm not going into the details here, but that's this kind of little oscillation, the Jupiter, the gas giants orbits can excite the belt to the levels that we see today. So the third idea, the third possibility is that the belt was born empty, fully empty, and refilled. So that in that case, you also should not have problems to make the small Mars. Because if the belt is empty, this is essentially the Hansen model, or you have a very truncated disk. So, but the question is how to refill the belt to have the asteroids that as we know today. So it turns out that asteroids, planetesimals, they might form only at very specific locations of the disk. So they like to form in regions where we have a very high gas to dust ratio, dust to gas ratio. So you have to very high density of solids to form planetesimals. And where a very peculiar location to the disk at the pressure bumps. Now they'll talk about this already today. So if you have a local pressure bump, so particles will drift inwards and they will concentrate in the disk, and then if you have a very high surface density of solids, then eventually you can form planetesimals. So this is what this simulation shows. So here is a simulation by Drazvoska, 2016, where she follows the dust growth up to planetesimal formation. And what she got is that maybe you can indeed only form planetesimals in very narrow regions of the disk. That's what the simulation shows. So this idea of having a very narrow disk, like the Hansen started, is not so crazy. It might make sense. So what we did was let's run simulations, very high resolution simulations, with a very narrow disk. So you put two Earth masses of material between 0.7 and 1 AU, and you have here Jupiter sitting at 5.34 AU, and have here the asteroid belt region. And so the gray bodies are the embryos, and the head ones are planetesimals. So let the simulation evolve, and that's what will happen. So the bodies, these are 50 simulations plotted together. The bodies start to interact with the planetesimals and planetary embryos, and eventually some planetesimals, the head guys, enter in the belt region. They are entering why? Because they get scattered by the planetary embryos. So basically this model provides what? Provides half of the belt. So far you get the C-types the S types. So the S types are water poor, so they can associate them with coming from the inner regions of the disk. So if you compare the kind of terrestrial planets that we get in this kind of model, that's what we have. So we have again the squares like the terrestrial planets, and the circles the simulated ones. So we can match quite well the 4 terrestrial planets in this model. And in terms of eccentricity and inclination distribution, that's what we have. So again, this is not a complete model because we can explain the masses of the planets, their orbits, and you can explain the asteroids in the inner part of the belt. But there's one piece missing: how to explain the C types from the other part. Because these two populations, the population in the inner part and the population in the outer part, they are different. So the origins of the C types will be addressed later in the talk. Why Mars is so small? And why the asteroid belts are so excited? So basically you have 2 different solutions. You can have a low mass belt or even an empty belt and have chaotic giant planets to excite the belt, or you can have the grand tack. So let's now address the origins of Earth's water and also the C-type asteroids in the belt. So again, we have that the inner region of the belt is dominated by S-types and the outer region is dominated by C-types. C-types, they are water-rich bodies, and these ones are water-poor. So we already implanted the S-types coming from the terrestrial region. So now we have to implant the C-types. If you look at this plot, so his plot shows the water mass fraction versus distance versus water mass fraction. So you have here different bodies in the solar system and the amount of water that they carry. So you have the TNOs that has a lot of water. They are mostly made of water. Have comets. Have the carbonaceous chondrites that has maybe a few percent of water. Have the ordinary chondrites that has a few percent, 0.1% of water, and they have the instantite objects that are pretty dry. So if you extrapolate this plot, this gradient, to the inner regions of the solar system, so you should expect this Earth should be drier than these guys. So that's the reason that it's important to invoke a scenario to explain the origins of Earth's water. So these bodies here, they are mostly located in the inner region of the belt. So if the bodies at the inner edge of the belt, they are dry, why not closer to the sun, that should be in hotter regions, should not be even drier? So that's the reason that we have explained the origin of Earth's water. So you have the grand tack. The grand tack proposed that the inner belt, the inner terrestrial region has water-poor objects, and the outer region has water-rich. And when Jupiter and Saturn migrate in the disk, they truncate the disk, and then when they go back, they scatter a lot of blue guys in the terrestrial region. That's what we can see here by these little points. And this is when water is delivered in the grand tack scenario. So this is another simulation showing this more clear. So here the green lines, the green circles are the orbs of the giant planets, Jupiter, Saturn. And then we have the water-poor bodies in the inner solar system, in the grand tack model, and the water-rich bodies in the outer solar system. And the giant planets are going to migrate inwards, as the grand tack proposed. Migrate inwards, and then they migrate outwards to near their current orbs. And we can see there's a lot of blue guys entering in the inner solar system. So that's when the water is delivered. So there's no problem in delivering water to the inner solar system in the grand tack. So there's a new mechanism that's not included in the grand tack, that should be included in any mode of terrestrial planet formation. That is the following. When you have a body growing around the sun, it sets the real radius. That's another talk about today. So that's the region where the planet dominates compared to the gravity from the star. So if a body gets inside the real radius of a larger embryo, for example, it's tended to be ejected or be accreted. So that's what happens when one body starts to grow and it disturbs the bodies nearby and eject them. So if you imagine that Jupiter was maybe a body that has maybe a few Earth masses of solid and then starts to accrete in gas to become a gas giant, planetesimals nearby should be disturbed and sent to everywhere. We run many simulations including this effect. We included 2 cores with a lot of planetesimals. We include gas drag. We make the giant planets grow. And you change a lot of parameters of the disk. I'm not going to the details, but I'm going to show the simulations that you make things much clearer. So here you have a simulations showing what happened when one gas giant is forming in the disk. So we have here Jupiter, Saturn. So we have here the asteroid belt. You have the disk of gas. So these bodies, when the simulation starts, they're going to feel gas drag, the small ones. So they tend to be, their centricities tend to be dumped, and they also tend to drift inwards. So let's see what happens. So you're going to assume that Jupiter, at this point, has 3 Earth masses, and Saturn also has only 3 Earth masses. And they're going to grow to their current size. So Jupiter is going to grow 100 times, and see what happens with these bodies nearby. They start to interact with these bodies, and when they start creating gas, look at this. It's raining in this inner solar system. What's happening is that bodies beyond Jupiter orbit get implanted in the inner solar system. So the same process repeats after the formation of the Saturn. So by this process, you can deliver water to the inner solar system, even to the Earth. So if you look at the source region of material that can deliver water to these regions, or C-type asteroids as you want, it's very wide region. And these regions probably has the snow line. So the snow line is probably somewhere between this region and the solar system. Maybe even inside there. So by this process, you can deliver water to the terrestrial region, because these bodies that has very high eccentricities, they will cross the orbits of terrestrial planets and collide and deliver water. So this process of delivering C-type material from the gas giants region to the belt is generic. It should happen everywhere a giant planet form, and it should play a very important role in the formation of the inner solar system. So if you compare the fraction or the relative abundance of material that can reach the asteroid belt in function of the different times of planetesimals, why this is important? Because gas drag depends on size. So planetesimals that are quite small, they feel a very strong gas, and they are typically implanted in the inner region, the other part of the belt, as you can see from the headline. So most of them are implanted in this region. If you look at the bodies that are very big, like 1,000 kilometer size bodies, they are implanted everywhere because they don't feel the effects of gas drag. So just to make it clear, so what happens is the following. When the body is feeling a strong gas drag, it's scattered and immediately is dampened. But it's not feeling a strong gas drag, it just keep going and keep having close encounters with Jupiter, and then is eventually implanted far away or closer in. So now you have a complete scenario if you combine the low mass asteroid belt with the injection of C-types. So this is the amount of mass that you have in the belt that are implanted during the process of formation of terrestrial planets. These are the S-type asteroids. And these are the C-type asteroids. As you can see, that you can get the inner regions being dominated by water-poor objects, and the other regions being dominated by water-rich. Where did the Earth's water come from, and where C-type asteroids come from? You can have the scattering of planetesimals during the growth of the giant planets, or you can have the Grand Tack. Have 2 different scenarios to explain. So let's summarize the solar system, the different views for the solar system formation. So you can have the Grand Tack model. So the Grand Tack model assumes that you have a very massive belt from the beginning. So if you have a lot of mass in the terrestrial region, have Jupiter and Saturn fully formed, and they're going to migrate. Jupiter migrates, truncate the disk, then Saturns come, and they go back and scatter the S and C types. By doing this, they can produce the terrestrial planets and can also explain the structure of the asteroid belt. The empty asteroid belt model, how it works. You assume from the beginning that there is no mass in the belt. And then Jupiter grows. S-types comes from the accretion of the terrestrial planets. And then maybe later, Saturn grows and populates a little bit more the asteroid belt with C-type asteroids. In the low mass, after this, they have to go chaotic to excite everything. So that's the reason that they have this swing. finally, in the low mass asteroid belt model, we have a low mass belt, as I showed here. So Jupiter grows, scattered inwards the C types. Saturns grow, they go chaotic in the excited belt. These are the views that we have for the formation of the solar system today. Maybe these two could be combined in the single one. Maybe this should be the most plausible idea. And you have, so you can say maybe not three, but we have two scenarios. So now let's focus on the older part of the belt, the older part of the solar system. So we want to explain why we have the ice giants. This is related to why did Planet 9 come from? So everybody here heard about Planet 9, I think, right? So this is a movie showing the orbits of some trans-Neptunian objects that could be disturbed by the presence of Planet 9. So so here you have the Sun, the 4 gas giants in the solar system. I'm going to plot the orbits of some trans-Neptunian objects that we have. Let's zoom out, because these objects are very far out. So that's what we get. So we have this population of objects. These are like trans-Neptunian objects, or like kilometer-sized objects, or like maybe much larger. And they have these very weird orbits. They're all clustered in a common direction, as you can see. And this is something that's not expected. If you're observing something and you have no bias, you should expect to have, and you have no perturbation causing this, you should expect to have a random distribution of bodies. But they are very confined in the same direction. The pericenters have the same direction. So to explain this clustering, Planet 9 has been invoked. Planet 9 is a hypothetical planet that has been proposed to explain why these objects are so clustered. So recently, a few new objects have been discovered, and they were predicted also by the Planet 9 perturbation. So these new objects, they have perpendicular orbits related to the plane of the Planet 9. So the possibility of Planet 9 being real, it's not negligible. So why not try to explore a scenario for the formation of this planet, of this potential planet? So you know that the ice giants of the solar system, they are very tilted. So Uranus has an obliquity of 98 degrees and Neptune of 30 degrees. So the most likely scenario to explain why they are so tilted is if they suffer collisions or giant collisions during the accretion. Because imagine that you have a collision, you just make them, twist them. So how this process might work? So let's take a look at the formation of the solar system again. So you're going to assume that the Jupiter and Saturn form in the solar system, and they block the formation, the migration of Uranus and Neptune, or the planetary embryos in the system. So we have here a population of planetesimal and planetary embryos. Eventually, this guy becomes Jupiter. Here you have a population of planetary embryos. And this population of planetary embryos, one of them is going to become Saturn, and the remaining ones should become the ice giants. Why they cannot migrate inwards? Because Jupiter is blocking the way. That's what we show in 2015. So when Jupiter blocks the way, they get dynamically stable because they get too close to Jupiter, and eventually they collide and grow. During this process of collisions, they grow to ice giants. And these collisions can naturally maybe explain why the ice giants has these large obliquities. I'm going to show a real simulation now of this process. Here you have a simulation of the formation of the ice giants in the solar system. Here you have Sun, Jupiter is fully formed, Saturn is assumed is fully formed. For simplicity, they are not migrating. And you have here a population of planetary embryos that have masses of a few Earth masses. So they're going to migrate inwards. And Jupiter is going to block them, Jupiter and Saturn. They start to migrate inwards, they scatter each other, they collide, and eventually we end up with a few planets. That's something like looks like the solar system. We have 3 ice giants. And during this process of formation of these 3 ice giants, some of them were ejected from the solar system. So here you have 3 ice giants, but you can ask, why do we have 3 if the solar system has only 2? That's another story. It has to do with the Nisi model, but I don't have time to go there now. But maybe you can ask later. So what we did was, let's get this scenario and plug it in the stellar cluster. The solar system was not formed alone in this. The sun was not formed alone in the solar in the molecular cloud. It has many stars nearby. So what we did was to simulate a stellar cluster with the solar system inside. The solar system is here in the center of this stellar. Each one of these points is one star, and the color shows the mass. So the cluster is going to evolve, and eventually it dissipates, and all stars get far away from each other. But during this process of dissipation, some stars can pass by the solar system. And so this is what matters for the next steps. Here's what we have. Imagine that we have the solar system formed in a stellar cluster. So let's zoom in the solar system. So here's the solar system. So we have here Jupiter and Saturn, and the planetary embryos that are going to form the ice giants. If this system becomes dynamically stable, and you have a star passing by, this star gives a kick to the planet. Because why this kick is important? Because otherwise the body is ejected and gets a more eccentric orbit and comes back to have another encounter with Jupiter and gets even more eccentric and eventually hits a hyperbolic orbit and decouple from the solar system. But if you give a kick at the right moment to a body that's on the process of being ejected, you can implant it in a different orbit that you allow to not have a next encounter with Jupiter. So that's what's going to happen here. So imagine that you have one body that's got ejected from the solar system during the accretion of the ice giants. So has a first kick and gets a little bit more eccentric. Get the second kick and get even more eccentric. The third kick, if you don't decouple the planet right now from the evolution with Jupiter, it's going to become hyperbolic. So what we do is, if you have a passing star nearby the solar system, it gives an external kick to the planet at this point, and then it changes its orbit to something like this. It can get more, maybe more circular. So that's what we did. We simulate this scenario in any-body simulations. Here we have again the solar system, the gas giants, have the planetary embryos, and they're gonna migrate as before. So you can see some stars crossing the solar system nearby. Look, these black guys here. So eventually, one of these guys ejected and received a kick and was implanted in this region. This could be a potential Planet 9 candidate. So Planet 9 could be produced in the solar system during the accretion of the ice giants. Let me show just one, because this is for the big fans of Planet 9. So the scenario is very similar, but at the end, you have not one, but 4 bodies here. I have to admit they are very eccentric, so they probably are not Planet 9s. But this is just to show how the scenario works. So this is the final episodes of the solar system formation. So we know that these giant planets, they form in disks. And during their formation, they tend to keep very low eccentric orbits, because the disk tend to keep them in a cold configuration. So here's the simulation of the solar system giant planets migrating the disk. So you can see that they tend to follow very eccentric orbit. In the meantime, Jupiter is opening a gap in the disk. So one of the questions is how the solar system giant planets, they get their current eccentricities. If during this process of formation, they should be circular or almost circular. And Jupiter has a eccentricity of about 0.047, I think. So it's not negligible. So how do you explain these eccentricities for the solar system terrestrial planets? So basically, at the end of the gas dispersal, Jupiter and Saturn, they should be in a more compact configuration, and with orbits with very low eccentricities. So here, we have 2 different views to explain how they reach their current orbits. One is the early dynamical stability. By early, I mean before the terrestrial planets are formed. So here they are in a resonant configuration, as predicted from the hydrodynamical simulations. And here we have the primordial Kuiper belt. So these bodies, they're going to interact with the primordial Kuiper belt, and they eventually become dynamically stable. something like this, boom, and they hit their current orbits. That's what probably happened in the solar system. But there's another view that proposed that the solar system was formed, the giant planets in the solar system hit their current configurations in a late dynamical stability, much longer after the terrestrial planets were formed, probably after 400 million years after the time zero of the solar system formation. So in this scenario, it's basically known as the Nisi model. We have the giant planets in resonant configuration, the terrestrial planets fully formed, the primordial Kuiper belt, and then this become dynamically stable and they hit their current orbits. So here is a real simulation showing this process. So we have here the four terrestrial planets, the four giant planets in the solar system. And you have a disk that represents the primordial Kuiper belt. So these planets, they are interacting with this population. So eventually, they will become dynamically stable and hit their current orbits. That's how probably the solar system was finally built. So you can see now the orbits are much more eccentric than before. The giant planets has two evolutions. They end up the gas disk phase probably in very cold orbits, and they hit their current configurations after maybe a few million years or even longer. So, but if you compare the solar system with most of the exoplanets that we know, the gas giants exoplanets, it's striking difference. There's a striking difference. Here you have the centricity distribution of giant planets in extrasolar systems. And here you have their distance from the star. Near you. And you can see here the blue guys are the terrestrial planets. Here you have these four ones here are Jupiter, Saturn, Uranus, and Neptune. And you have these guys with very high eccentric orbits at height as 0.8. So why the solar system is so different from them? If most of the gas giants that we know has very eccentric orbits. Why is that? So maybe this is the cause. Maybe in these systems we have a few gas giants, maybe 2 or 3, and you have again this disk that could be associated with the Kuiper belt of the solar system, and these inner regions that could be associated with the terrestrial regions of the solar system. But you have 3 exo gas giants. So let's evolve the system to see what happens. So eventually, as in the solar system, they become dynamically stable. But the process is much more dramatic. Now, that's what happened. So you can see that's clearly different from the solar system. So, and at the end you have planets with a 0.8 of eccentricity near a few waves. So why the solar system did not get so eccentric? The reason for this is why Jupiter and Saturn did not have close encounters. The gas giants that I showed before had close encounters during their evolution. If you have Jupiter and Saturn having close encounters, that's the typical eccentricity of Jupiter. If you don't have, that's the typical one. And this is the plot showing the eccentricity of the gas giants in extrasolar systems. So maybe by avoiding having close encounters with Jupiter, Jupiter became an atypical gas giant and started looking like this. And also this might have, as you could see in the previous animation, this might also have made possible the formation of the inner solar system. Let's pay attention again what happened to these guys here. So these should be the terrestrial planets in the solar system only. So there's nothing left to form terrestrial planet later. So maybe this could be a disaster in terms of formation of terrestrial planets in extrasolar planetary systems. So this shows that solar system may be a little bit atypical. To conclude, we have different views to explain the solar system today. We have the Grand Tack and the low mass asteroid belt. We cannot tell yet which model is better. Maybe in the future. If Planet 9 exists, it might be a large planetary embryo that gets scattered during the accretion of the ice giants in the solar system. By avoiding multiple close encounters, Jupiter and Saturn may have avoided the destruction of the inner solar system. That's where I stop.